In the name of Almighty God, I'm Asa Sankasha, and today I want to talk about chemical reaction engineering module in consumer physics simulation software. Now I want to go through the laminar two-phase fluid, the laminar two-phase fluid version of the vapor liquid equilibrium multiphysics interface is used to simulate evaporation and condensation to or from a vapor liquid interface and to track the position of the interface. The interface combines the transfer of concentrated species in vapor, the laminar flow, and the moving mesh interfaces. The reacting fluid multiphysics coupling, which is added automatically coupled vapor mass transport and fluid flow. Now I want to go through the turbulent fluid capsule. The turbulent fluid capsule version of the vapor liquid equilibrium multiphysics interface is used to simulate evaporation and condensation to or from a vapor liquid interface. The interface combines the transport of concentrated species in vapor and the turbulent fluid capsule interfaces. The reacting fluid multiphysics coupling, which is added automatically, couples vapor mass transfer and turbulent fluid flow. This interface requires a license for a safety module or the heat transfer module. Turbulent fluid capsule. I read it, and now I want to go through the turbulent fluid omega. The turbulent fluid omega concentrated species version of the vapor liquid equilibrium multiphysics interface is used to simulate evaporation and condensation to or from a vapor liquid interface. The interface combines the transport of concentrated species in vapor and turbulent fluid omega interfaces. The reacting fluid multiphysics coupling, which is added automatically, couples vapor mass transport and turbulent fluid flow. This interface requires a license for CFD module. Now I want to go through the turbulent fluid SST. The turbulent fluid SST version of the vapor liquid equilibrium multiphysics interface is used to simulate evaporation and condensation to or from a vapor liquid interface. The interface combines the transport of concentrated species in vapor and turbulent fluid SST interfaces. The reacting fluid multiphysics coupling, which is added automatically, couples vapor mass transfer and turbulent fluid flow. This interface requires a license for the safety module or the heat transfer module. Turbulent fluid low Reynolds curves epsilon. The turbulent fluid low Reynolds curves epsilon version of the vapor liquid equilibrium multiphysics interface is used to simulate evaporation and condensation to or from a vapor liquid interface. The interface combines the transport of concentrated species in vapor and the turbulent fluid low Reynolds curves epsilon interfaces. The reacting fluid multiphysics coupling, which is added automatically, couples vapor mass transfer and turbulent fluid flow. This interface requires a license for safety module or the heat transfer module. Now I want to go through the reacting fluid concentrated species multiphysics interface chapter. Reacting fluid concentrated species is a predefined multiphysics interface available in the chemical reaction engineering module that groups fluid flow with mass transport and reactions. Selecting laminar for concentrated species under the chemical species transport, then select reacting fluid branch of the model result or at physics window. A laminar flow interface and a transfer of concentrated species interface are added to the model builder. In addition, the multiphysics node is added, which includes the multiphysics coupling feature reacting flow. The reacting flow feature predefines and controls the coupling between the separate interfaces in order to facilitate its setup of models. In this section, the reacting laminar flow concentrated species interface, the reacting flow coupling feature, physics interface features. Now I want to go through the reactant laminar flow concentrated species interface. The reactant laminar flow multiphysics interface is used to simulate laminar flow couped to a species transfer in a gas or liquid. It combines the laminar flow and transport of concentrated species interfaces. The reactant flow multiphysics coupling, which is added automatically, coupled fluid flow and mass transport. The fluid flow can either be free flow or flow in a porous medium. The species transfer supports both a mixture where the concentrations are of comparable order of magnitude and low concentration solutes in a solvent. The interface can be used for stationary and time-dependent analysis in two-dimensional axis of symmetry and three dimensions. On the constituent physics interfaces, the equations solved by the laminar flow interface are the Navier-Stokes equations for conservation of momentum and continuity equation for the conservation of mass. A fluid properties feature is active by default on the entire interface selection. A porous medium feature can be added in order to model flow in a porous medium By solving the Brinkman equation, the transfer of concentrated species interface solves for an arbitrary number of mass fractions. The species equations include transfer of by convection, diffusion, and optionally migration and electric field. The reaction laminar flow interface triggers pseudo-time stepping for the fluid equations. When used, pseudo-time stepping for stationary equation form in the fluid flow interface is set to automatic from physics. The reacting fluid coupling feature uses the reacting fluid multiphysics coupling to simulate mass transport and reactions in a gas or liquid mixture where the fluid can be dependent on the mixture composition. When a heat transfer and a chemistry interface are selected, use this coupling to simulate heat transfer additionally to mass transport and reactions. The coupling adds the heat source of reaction when a heat transfer surface is selected. No additional source needs to be defined to account for it in the heat transfer interface. It also accounts for the multiphysics stabilization terms for work due to pressure forces and viscous dissipation. Select a fluid interface and a species transport interface to couple fluid with mass transport, chemistry, and heat transfer are optional. They can be set to none when the coupling is used to simulate isothermal mixtures. When a chemistry interface is selected and heat transfer is set to none, fluid properties are taken from the chemistry interface, set the temperature to evaluate the fluid properties, synchronized with all physics interfaces at the given temperature. Select the chemistry interface and heat transfer interface in order to account for the heat of reaction, enthalpy, diffusion, viscous heating, and mass fluxes contributing to the heat and energy balance. When the chemistry is set to none and the heat transfer interface is selected, the coupling is solved in the same way as when no heat transfer is selected. Thermodynamic properties are required by the heat transfer interface. The pressure velocity and temperature variables of the reactant fluid coupling node are set to common model input values of the default model inputs node on the complementary selection. That is, all domains except those from the selection list. It allows to couple multiple fully flow transfer of species interfaces with a single heat transfer interface. See default models inputs in the Comsomol Physics Reference Manual for details. Now I want to talk about domain level synchronization. The reacting fluid coupling synchronizes the features from chemistry interface, heat transfer interface, single phase fluid or Brinkman equations interface, and transfer of concentrated species interface. When chemistry interface is not selected, the density in the single phase fluid interface is automatically synchronized to the one defined by the transport of the concentrated species interface. The velocity field used by the transport of concentrated species interface and heat transfer interface is synchronous to the one computed in the single-phase fluid interface. When a chemistry interface is selected, the reacting fluid coupling synchronizes the definition of the thermal conductivity, density, heat capacity, enthalpy, and dynamic viscosity with the order coupled physics interfaces. The reference temperature is taken from the heat transfer interface. The Stefan velocity, the reacting fluid coupling feature, automatically couples mass transfer on boundaries and applies a corresponding velocity contribution for the fluid, prescribing a net mass boundary flux in transfer of concentrated species interface, either using a flux or mass fraction feature. The reacting fluid feature computes the Stefan velocity and applies these in the wall features using the same selection. Mass transfer to the other phases in porous media when coupled to the Brinkman equation interface, the reacting fluid node automatically computes the net mass source or sink in a reaction when mass transfer to other phases is enabled. Node in the transfer of concentrated species interface and adds the corresponding source sink to the momentum equations of the fluid and matrix properties domains. Now I want to go to the turbulent mass transfer. When a turbulent model is used, the reacting fluid coupling applies turbulent modeling for the mass transport in the following manners. Turbulent heat transfer and mass transport are added, defined from the turbulent viscosity and the turbulent Schmidt number. For more information, see the turbulent mass transport model, temperature and mass transport wall functions. When turbulence model using the wall functions is used for the fluid, the reacting fluid coupling automatically adds wall functions for the temperature and mass transfer of the some and same boundaries. For more information, see mass transport Wall function. Settings section. The label is default. Multiphysics coupling feature name. The name is used primarily as a scope prefix for variables defined by the coupling node. Refer to such variables in expressions using the pattern name.variable name in order to distinguish between variables belonging to different coupling nodes or physics interfaces. The name string must be unique. Only letters, numbers, and underscores are permitted in the name field. The first character must be a letter. The default name for the first multiphysics coupling feature in a model is a near one domain selection. The reacting fluid coupling is automatically defined on the intersection of the selection for the coupled surfaces when modeling porous media. Transport a more porous media feature applied on the same domains is needed in all coupled transport interfaces. Reacting fluid coupling supports porous media transport in the fluid flow and species transport interfaces. The selection list displays the domain where the coupling feature is active. Coupled interfaces. This section defines the physics involved in the multiphysics coupling, the fluid flow, species transport, chemistry, heat transfer. Lists include all applicable physics interfaces. The default value depends on how this coupling node is created. If it is added from the physics ribbon, Windows user, physics contextual toolbar, Macintosh or Linux users, or context menu for all users, the first physics interface of each type in the component is selected as the default. If it is added automatically when a multiphysics interface is chosen in the model wizard or add a physics window, then the two participating physics interface are selected. You can also select none from a list to uncouple the node from a physics interface. Click the go to source button to move to the main physics interface node for the selected physics interface. Click the show or hide physics properties settings button to toggle the display of physics properties settings affected the coupling feature. When the turbulent model is used, turbulent heat and mass transfer is automatically accounted for. See the settings in turbulence section below. Using reacting flow, the heat and mass transfer treatment as walls flows that apply for the fluid flow. Therefore, the wall treatment setting is also displayed when using a turbulence model. For more information on turbulent mass transfer at walls, see the section Mass transfer wall functions in the CFD module user's guide. If a physics interface is deleted and then added to the model again, then in order to re-establish the coupling, you need to choose the physics interface again from the fluid flow, species transport, chemistry, and heat transfer list. This is applicable to all multiphysics coupling nodes that would normally default to the once present interface. See multiphysics modeling workflow in the Custom Multiphysics Reference Manual. Thank you so much for watching my tutorial video until the end. Today is 17th of May 2026. Time is 8:32 a.m. You can download the related file from github.com/masterscript.